we're going to get started. So, thank you for coming to today's meetup. This is our first, and hopefully others will follow, Data Science Student Showcase. So this has been a long time in the making. I've been working with Mike for about over a year to try to make this happen, so I'm very happy to be here. I'm very happy to have the speakers. Thank you for coming. So tonight we have 4 speakers. I'll go over the speakers once we get to the bio on a number of topics. Before we get started, I always like to thank the sponsors. They really help make this possible. So, it works. I will stand here. So, Vera Technologies. They're a defense contractor, so they've been sponsoring the meetup for about 6 or 7 years. So there used to be another meetup, Data Science MD, that I ran, and now it's this one, but they've been supportive for many years now. They're kind of like a... Test. Okay. So Baron is a defense contracting company. They're considered small, but they're a little larger. So if you're interested in that opportunity, please reach out to me and I'll introduce you. Applied Technology Group is another defense contractor. There's going to be a theme here in a second. They've been sponsoring for several years now. Usually Eileen's here to introduce herself, but if you're interested in data science, software engineering, system engineering, and you would like to learn what they're doing, talk to me and I'll introduce you. Clarity is a defense contracting company. They are looking for software engineers, system engineers, DevOps engineers, system administrators, platform engineers. They are hiring. Everyone's hiring, by the way, so if you want a job, just let me know. That'll be key in a second. Next Century is another defense contractor. They're a little well-known, or a little more well-known. They're larger, very, very successful company. They do a lot of their own events, so they have this Women in Computing event that they do periodically. I have some information if you're interested. So Miner and Cash is not a defense contractor. They're actually a data science consultant firm. So they do a lot of unclassified work up and down the East Coast. They kind of are like a data science boutique. They used to be willing to work with some folks that wanted part-time work, but if you are actually looking for an opportunity to work in the non-cleared space, and you're interested, like if you're the students that are graduating, I would say reach out to me and I can introduce you. Don's a phenomenal guy. He runs the company and he's a wealth of information. He can probably give you some pointers where you should go. Ares Ventures is my company. We're a defense contracting company. We're a little small. We're at 3. So if you're interested in learning more, just talk to me and I'll be more than happy to talk about myself. Towson is our venue. Very honored to be here. Mike, would you like to talk about the program? Not a defense contractor.
Hi, I'm Mike McGuire, and I'm an associate professor here at Towson. And I contacted Jason back in I think it was maybe 2 years ago. It's been a long time. This event has been a long time in the works, just because I'm trying to find the right time for it when the semester's not happening. Because if you think it was crazy getting here tonight when the semester's in full swing, this would not be happening. But we just started a data science track in our Master's in Computer Science here at Towson. And so, we were kind of looking to fill an adjunct professor role. So I contacted Jason, and he asked me if maybe we would host an event like this. So welcome. I'm glad that you guys are here. One thing that I want to thank you that I don't have a slide for, but the Towson School of Emerging Technologies, Dr. Heidi Fung in the corner back there. She's graciously volunteered her time to help with this event tonight, which I'm extremely thankful for because I needed the extra support. They provided the pizza, and their admin actually got the space for us. So I want to thank everybody for showing up. I want to thank our student presenters, and I'm really looking forward to seeing the presentations tonight.
Thank you, Mike. So just some brief announcements. So if this is your first time to the meetup, Is this anyone's first time to the meetup? Yeah, it usually happens. So if this is your first time, we do this every month, but it's always in different locations. They tend to be a little more further south in the Laurel, Columbia, Baltimore area. Next month, there is a speaker discussing computer vision. And then in July, we are actually having one of the chiefs of Cyber Command talk about some of the analytic work they're doing. That will be down at the Hanover, Maryland area. We have a newsletter. You can sign up at news.dataworksmd.org. It's usually like local information, events that are of interest, usually related to the sponsors, discounts for conferences, things like that. O'Reilly likes to give me a lot of free stuff and discount codes. All sponsors are hiring. If you're interested, let me know. Even if you're interested in other work, just let me know, and I keep a log of everyone that's interested, and then if anyone is looking for folks, I can kind of make the connection. If you're interested in doing work with the meetup, speaking or helping or working on a side project, just contact me at info@dataworksmd.org. And that is it. So now I will introduce the speakers. So tonight we have 4 speakers. We have Sean Donnelly talking about Elasticsearch for business intelligence and application insights. He's an MS in computer science. If you noticed in the back, Elastic is really good at this. They must monitor all the meetups, and once someone talks about Elastic, they stalk them, and then they ask for them to give away free stuff. So there's free stuff in the back from Elastic. Jon Patton, machine learning for requirements engineering. He is an undergraduate in computer science. Tian is a doctoral student in AIT, and he's discussing an asynchronous distributed deep learning based intrusion detection system for IoT devices. Sounds pretty awesome. And then Tian is a master's in computer science, talking about Fortune 500 company performance analysis using social networks. So with that, I'm going to introduce or hand it over to Sean. I kindly ask that you wait to the end to do the questions. He has a slide for that. I do have a free t-shirt and a free book to give away at the end. The way I do it is if you ask a question and you're the first one to get to me, you get your pick. And that's it. Thank you very much.
All right. Thank you everyone for having me. I'm really happy to be here and be able to present and talk a little bit about Elasticsearch. So a little bit more about me. I'm a software architect at Cyber for All, which is a research group here at Towson University. So I've been with the research group for about 2 years now. And this talk is actually going to stem out of the work that I do there, not so much work that I've done in the classroom. So a little bit of variety here tonight. You can find me on Twitter and really anywhere on the internet at Donnelly. My GitHub is also up there if you want to check out any projects that I'm doing on there. But feel free to reach out and talk to me if you have any questions about things that I discussed today. You can find me pretty much everywhere on the internet at Donnelly. So a little bit about what we are going to cover and what we're not going to cover, since it's a little bit condensed of a presentation here. We're going to talk about Elasticsearch from the very basics. We're going to look at fundamentals of storage and retrieval of documents in Elasticsearch. We're going to figure out really why the Clark team chose to use Elasticsearch. And then from there, talk a little bit about the full Elastic stack, going beyond just the Elasticsearch product, integrating other products as well, and building out a full stack, integrating data pipelines with that, figuring out how to draw some meaningful insights from the data that you have. We're not going to be able to get into clusters, nodes, scaling, all of the nitty-gritty that goes into really setting up and getting an Elasticsearch cluster running in production. We're not going to be able to talk about the details of actually piecing together the Elastic Stack, but I hope that from this you're able to see the excitement that I have in working with the Elastic Stack and see how that might fit into any needs that you might have. So first off, what is Elasticsearch? The really simple way to put it is a RESTful search and analytics engine. Each of these words is going to be pretty key when it comes down to it. The fact that it's based on REST and that its primary focus is search and analytics is going to come into play a little bit later. So what does it do? It uses Lucene indices under the hood So some of you might be familiar with the Apache Lucene project. Under the hood, each Elasticsearch node that forms your entire cluster is a Lucene index. And so what this provides is built-in tokenizers, analyzers, etc., that we're able to use when we're indexing our data. So as we're putting our data into Elasticsearch, there's a lot that we get out of the box, and with just a little bit of specification saying I want to use this analyzer, this tokenizer, we're able to get a really robust index put together very quickly in which we can perform some really awesome and powerful search. And we don't have to spend a lot of time writing that all ourselves. However, if we want to write that ourselves, it also gives us the ability to create custom tokenizers, custom analyzers. We also get a score for the relevancy of each result to the query. This was really important when we were deciding on switching over to Elasticsearch for our search engine inside of Clark. Clark being the main project that the research group has going. I actually realized I skipped right past that in my introduction slide. But Clark is a cybersecurity digital library. And so what that means is we host a wide variety of curriculum for cybersecurity faculty. And so faculty put curriculum in, and then other faculty can take that curriculum out. All of that curriculum has a whole bunch of metadata mapping to different academic standards and guidelines. And so really our main use case is a professor at a university who doesn't have a lot of investment in their cyber education program is able to go and pull out some really great lab activities or even full courses they can then integrate into their own courses that they're teaching at their university. And at the end of the day, we look at it as if we can increase across the board the quality of curriculum at each university, then we will be securing the nation as all of our graduates who are coming out of our programs are going to have a little bit more proficiency. So quick backtrack there. Now coming back to what I'm talking about here with what does it do. This is all from the lens of us making our decision at Clark to use Elasticsearch. We get a score for each query right out of the box. That's something that requires no configuration at all. And we also have the ability to just get binary matching. So if we don't care about that score, we can just say, does this match my query or not? Pagination also right out of the box. That's kind of the theme that is underlying all of this. If we get into how to index a document in Elasticsearch, this is kind of coming back to the RESTful API that we have. So all of Elasticsearch is done over HTTP, making requests to our Elasticsearch cluster. And so this makes it really easy to get set up and running on your local machine, in a cloud environment, etc., because all you have to do is start firing off some put, some posts, some GET requests, and you're able to start indexing data and retrieving that data out. So if we would want to go ahead and put a meetup into our meetups index, we could name it DataWorksMD and we could give it a date. So very trivial case for a document here, but we'll notice that it's a JSON blob and we're simply making a put request. We're going to have the index specified up in the URL since the system is RESTful. So meetups is the index that we're working with. We're going to be putting a document in there and following proper REST protocol, the fact that we're using a put means that we are specifying the ID on the server. And so we've tacked that on at the end of the URL. And so we're giving this document an ID of 1. So to pull it out quickly, all that we have to do is hit that same exact URL that we just put data at with a GET request. And we'll notice that a good bit more comes back from Elasticsearch than what we put in. We get to see some metadata that Elastic has generated for us. The really interesting aspects here are we get to see the index. That helps us with understanding where our data is coming from if we're using multiple indices. We see that the type is a document. We can store lots of different types. This is just a plain document that it's inferring the shape of. But we also get a version number by default here. So if I index again, if I put more data in there, it's going to actually increment that version count. So we can track that version. And then here, it's giving us that source document. The same exact JSON that we put in verbatim is going to appear. Now, if we want to search for that document, maybe we don't have the exact URL, we maybe don't know the ID. What we have is a search query that's provided by our users. So here, we can send a GET request once again to the index that we're working with, which is meetups, and we can just hit the search endpoint on that index. So following that RESTful structure, we're providing a query string here. It's a little hard to read just because it's all going in the query string on the URL, but the idea here is we send a name, DataWorks MD, and when we send that over to Elasticsearch, we get a whole bunch of information back. I'm just showing a subset of it up on screen here because there's a little bit too much to show. What we really care about is the hits. So here we see that the relationship in this document that came back is equality-based. So it was able to find a document that has the exact name of DataWorks MD, and it's giving us a score for the relevancy of that document based on the information that it has. So here now, if we have maybe multiple meetups that are all indexed here, we're going to have a way to rank them right out of the box in our search results on our webpage. So Elasticsearch at Clark, the goals that we had were we were needing to create a new search pipeline. Our search was sluggish. It was not really returning sensible results, and we were doing a lot of work all to get to that point where it was sluggish and we weren't really getting sensible results. So we were just relying on querying that we could piece together with the database that we were using. And so our goals were to speed it up. We wanted our search to be faster. It's really at the core of content discovery on our system, is being able to search through that content and find what you care about. Cybersecurity has a lot of terminology, there's a lot of specifics, and so just a plain browsing interface isn't necessarily going to give you the speed of retrieval if you're looking for something like SCADA-based VMs. So if you're looking for these really specific things, you're going to need search. That search needs to be fast, otherwise you're probably going to navigate away, you might go somewhere else. We wanted full text search as well. It was kind of hard to do with the way that we had our data structured originally using MongoDB. But we knew that whatever we were going to do with our search pipeline, we need full text. And we also needed to keep the word stemming, the stop word identification, and fuzziness searching that we had built. So these three things, the word stemming, stop words, fuzziness, was something that we had built an entire Node.js service to be able to do this based on the queries that were coming in from our application. And it was kind of hard to maintain. We'd run into certain vulnerabilities on NPM using different packages. And it was just a lot of work for something that our team wasn't very specialized in. And so when we found Elasticsearch, we realized that we could get a fast search, a really blazing fast search. We could get full text search as well as it could take care of all these things out of the box. And so we could defer all of that work over to the experts at Elastic who are able to really build this wonderful product. A quick note on speed, which blew me away recently when I was talking with a software architect who works at a financial analysis company, I think is the way that we would put it. They had some reports that running in Postgres were taking about 3 to 4 days to complete and actually run and generate those reports. When they moved all of that data over to an Elasticsearch index, they were able to complete that in 7 hours. So there was quite a bit of a difference, and they're now able to run those reports much more frequently and have a lot more iteration based on the data that's coming back. That's really moving their business further ahead. Coming back to why we decided to use Elasticsearch here at Clark, another thing that just made it easy was that we already were using MongoDB, and so we were storing our documents in this JSON-like structure already. And so simply pulling something right out of Mongo, we were able to index it verbatim into Elasticsearch. We were able to use IDs that we already had generated, and things were able to really flow there. And it also worked really well with reducing the complexity of the task, that all of our searchable data in our system was immutable. If you were going to modify that data in any way, logically, according to our application's rules, you would have to actually make a new copy of that. You'd actually be creating a new version entirely. So it worked really well for not having to deal with some of the downsides that you get with working with a pure index, where you don't necessarily have full ACID transactions insured right out of the box. what this came to look like is the architecture diagram that you see here. So we started off with having our client application, which is really represented by this section of the diagram here. We have an Angular app and then a backend that specifically works on aggregating other backend services to present those to the front end. This was talking entirely with this one service right here, and that service was what was really becoming problematic. And it was performing all of the search out of MongoDB here. We switched over to Elasticsearch. We were able to index our submissions and our finalized published materials into 2 different indices, and then put together a very simple search service just for some business logic there. So we stood this up rather quickly, and that's one of the really key things that impressed me with Elasticsearch, was that we were able to put together this architecture, stand it up in production, and get that running very fast. The Elastic products were just really a joy to work with. Their documentation was great, and they did a lot of work for us, and that was something that we really liked, because we're a team fully of software engineers, and none of us were really experts when it came to search. And so we started digging in more to Elasticsearch and what we liked so much about it. We started to realize that there's much more than just Elasticsearch out there. Elastic, as a company, has actually built a fantastic suite of tools. And so if we were able to provide application search, what else could we potentially do with these powerful indices that we're able to search data at blazing fast rates, and we're really just able to give us a lot of power? We started out by using Kibana, which is another service by Elastic. And Kibana is just a visualization layer, so it just queries your Elasticsearch indices, allows you to put together dashboards and other types of visualizations of that data. And so we started exploring the data that we had indexed in production, and we started to discover a lot of interesting facts about that data. What was happening at what stage of the life cycle for this course material. And from there we started thinking, what else could we actually do here? What could we sort of funnel in? Working with Elasticsearch, working with Kibana has been a really fantastic flow for our team. Well, why not actually integrate our logs or something else with that as well, that we could get a little bit more in terms of understanding what's actually happening with all of the services that we had running in production. We had services running on lots of different processes, and so we wanted to understand our application metrics across those. So the Elastic Stack is something that we've started digging into, and that's really the core of my talk here, is that I'm very excited about this. It's a breeze to work with, it's really a joy, and it provides a ton of power. So the basics of the Elastic Stack, you'll hear it referred to as the ELK stack for Elasticsearch, Logstash, and Kibana. The gist of it is that Logstash allows you to ingest data into Elasticsearch, to take in some form of input, to transform it in some way, filter out data, and then output it into Elasticsearch. And then Elasticsearch is where you have your data stored in those indices. You're able to search on it and perform different types of analysis. And then at the end, you're able to pull up a visualization dashboard. You're able to have graphs that you're able to send out to different teams. So everyone can have a good real-time, or almost nearly real-time understanding of what's going on inside of your system. What gets even more interesting, really excites me as a software engineer, is that it's built in a way where all of these services are very modular and tie together pretty nicely. So when you're working with Elasticsearch and Kibana as your storage and visualization layers, you can also do a lot of other things to get the data that you're working with into Elasticsearch. So Logstash is one of the ways that you can ship data into Elasticsearch and be able to transform it as it's going in. FileBeats is another way that you can actually ship files. So those are particularly log files or other pretty massive data dumps that are stored somewhere. You can also write entirely your own data pipeline. There's a RESTful API. So there's the single document indexing as well as bulk updates. And so if you have your own custom pipeline already, you can just plug that right in and have that start indexing in Elasticsearch, and then be able to use a lot of the really fantastic tools that Elasticsearch and Kibana provide. It's also really nice that they have not only the Elastic Cloud, if you're into more of a SaaS offering, if you need somebody else to be in charge of that, or it's self-hosted as well, it's fully open source, so you can just get an Elasticsearch node up and running on your laptop. And that was one of the fantastic things that really let us start working with it quickly, was we were able to quickly set up our infrastructure the same way it would run in production, just running on our laptop. So to kind of bring this around to the key use cases that really have me excited about Elastic and the stack that they've provided, the takeaways that I hope that you all have in terms of the different use cases that you can find for application insight as well as for business intelligence. If you're able to get data into these high-performing indices, yes, you can go with sort of the base case, which is application search, and you can bring that into your system pretty easily. But there's a lot more that we can actually do with the Elastic Stack in terms of performance monitoring for our systems. Just reading those log files, indexing those log files, we can have an understanding of how our response times for our web APIs slowed significantly. We can understand the logs that we honestly never read about our application. We can have those put into ways that humans can easily understand them and digest that information. There are plenty of pros out there who can sift through a giant log file and find something meaningful, but if we can give our developers a dashboard, a visualization to look at, that's so much more powerful because we're now enabling just about everyone on the team to start understanding how our applications are talking to us on a daily basis. There's also some really fascinating things that we can do with machine learning built right into Elasticsearch. We can actually spin up machine learning nodes that are able to answer some questions and reach out to us and actually let us know some things like, hey, if there's an unusual increase in abandoned shopping carts in my e-commerce application, then I want an alert to go directly out to me. If there's an unusual change in status codes, maybe our login route is throwing a lot of errors, and we might want to know that that's not normal, something happened. We can tie that back to a new deployment that went out. There's a lot of different use cases that we can find for Elasticsearch. I think at the end of the day, the really powerful thing behind it is the way that the indices have been able to perform, the speed at which they're able to perform has just sort of opened it up to how can we plug and play between Elasticsearch and Kibana and really put together some fantastic visualizations and get some understanding of what's going on in the data. So thank you all for your time. I think we now have time for questions.
Do like one question, and then we'll do one question, and at the very end we can see if there's time that everyone can ask any questions.
Question?
Do you guys use Elastic.io or the Amazon Community Elasticsearch?
Yeah, so we're using the Amazon community distribution of Elasticsearch just as all of our infrastructure was already in AWS, and we've enjoyed it. It's really not been a problem for us.
Thank you. So next up is Jon Patton talking about machine learning for requirements gathering. So like I said, at the very end, if you have additional questions, you could go up to the speakers and ask.
So this was an independent study project I had this semester, it was like half this semester. And what's happened is we're given an unlabeled, unsorted data set that is probably about software engineering in some fashion. And what we would like to do is we would like to go through this and label certain aspects of the sentences. So there's two different types of software engineering requirements, and we'll go through those in a second. But right now, this is a task that has to be done by humans, and humans can even disagree about the right way to label things. So those are some of the main challenges with this. So here's our two types of software requirements. NFRs are non-functional requirements. They're a set of requirements that you can define as a canonical set. So things like security and usability, maintainability, sort of overarching aspects of the software that don't have anything to do with the way the actual software product is processing anything. They're things that you can call them categories for any software project. Functional requirements, on the other hand, are going to be related to a specific project. They're not going to be, you're not going to have generalized labels for them, and those are the ones that are even more difficult to categorize. There's been a lot of work to automatically categorize non-functional requirements, and this project was given to me by Drs. Dellinger and Dang here in Towson, and they had done some work on previous semesters in categorizing non-functional requirements, and they said, hey, let's see if we can do it with functional requirements too. If you want the sources for some of this stuff, there's a paper too that I can give you. So if you want sources, I'm trying to get that on the slide. But so this is a text classification problem. So what we're going to need is we're going to need some tools for classifying text. And there's lots of natural language processing libraries out there. I decided to go with GenSim, which is a pretty popular and powerful library with lots and lots of built-in functionality. One of the main things we're going to need, though, are word vectors. And we'll have a whole slide on what those look like. But they're ways to turn words into just a vector so you can do math with it, which is pretty nice if you want something a little better than just looking at words by themselves. There's a very old type of text processing called bag of words. Bag of words is every time you come across a new word, you put it in your bag. And then if you want to see whether a sentence contains something that's in your bag, you just look through the bag and you see if the word in the sentence is in the bag. It has a lot of problems, one of which is that you have to account for, say, words that are very, very similar, but not identical, words that have endings on them. So app, as in short for application, and apple, app might appear in the word apple, but it's not the same word, right? So you have to be careful about some of the stuff with bag of words, but it does get used a little bit in the model that we're going to use. And stemming is a process where you take longer words and you shorten them into something. So processing, you can shorten it to just process. Chop off the ing ending. This is something that was used a lot in spam classification, for instance. Stop words are the words that you want to, they appear very often in sentences. They're connecting words, conjunctions, and, but, then, simple words that don't really give you any good semantics or context or information. They're just words that you want to get out of the sentence. And you can also define your own stop words. So if you know that a particular word appears very, very often in your corpus, your collection of documents, you can just tell your model, hey, let's never ever pay attention to that word. Every time we come across it in the corpus, we're going to ignore it. And stripping is just taking out extra spaces, extra commas, punctuation, numerals. So here's word vectors. Stanford developed a model called GLOVE. It's sort of an, I don't want to necessarily say that it's an improvement, but it's a variation of the word-to-vec model that Google developed in 2013. If you're very, very interested, Stanford actually has their entire natural language processing course online, and they have a whole lecture and homework assignment on GLOVE where you can learn how to do it yourself. But they have provided several versions of their GLOVE vectors. The ones I used for this project are the largest vectors. They're 300 features, so it's a 300-dimensional space. It's trained on 800 billion tokens from a web crawl. So much, much, much more information than I could have gotten on my own. So these are very well-trained vectors. They've seen lots and lots of words. And the basic principle is that every time you come across a new word, it gets a one-hot encoding somewhere in the vector. So somewhere you've got a whole vector of zeros, 0, 0, 0, 0, 0, and then there's going to be a 1 somewhere. And as you train the model, when words appear next to each other, you can collapse 2 or 3 words down into a vector so that you have a 1 in more than one place. And eventually, as you go through the corpus, the vectors will learn what words they appear next to and what words appear next to them, not necessarily considering a word in the middle, but words on either side. And eventually, you'll get to the point where you have vectors that understand some context about what appears around them. I'm going to skip ahead to this slide. So this is one of Stanford's example vector spaces, or vector representations. So you can see down here we have king, and up here we have queen. So these are 2 different points. These are the vector representations of 2 different points. You can see that words that are male are down here toward the bottom, whereas words that are female are up here toward the top. So empress is up here, emperor all the way down here. And the spaces between those vectors are learned from the way that they train the GLOVE model. All right. So the second tool we need was topic modeling. So this is built into GenSim. I chose to use latent semantic analysis, right? Indexing, which is based on latent semantic analysis. There's a few different types of topic modeling you can use, but this one produced almost the same results every time I did it. Some other models don't do that. And for this project, I wanted it to be repeatable. It was a little more important that it was repeatable than maybe simpler or faster. We'll go through. I'll show a little bit. There's a little bit more information in this presentation than I needed for this project, but I'll show you what it looks like when I say the elements are weighted. So GenSim spits out some topics for me, and when you go through the corpus, you're going to find that there are some words that are very, very important to a topic, and it's going to have a high weight, and these are going to be ordered. So the first word and the first weight are the most important to the topic, and then the second topic, if you want a second topic, will be weighted similarly. Third topic, and you can keep going until you no longer want topic. So you can specify exactly how many topics you want. You can also specify how many words you want in each topic. And as you go through, you're eventually going to end up with some topics that hopefully match up with some sentences. In our case, since we're trying to classify software requirements, our hope is that the words picked for the topics will have to do with a specific software requirement, and in particular a specific non-functional or a specific functional requirement, because there might be some other way to label a non-functional requirement, but the functional requirements, we don't have any way to identify it ourselves without going through and reading all of the requirements. I mentioned bag of words earlier, and so we don't need to go over that slide. Cosine similarity, I showed the slide for this earlier, but cosine similarity is a way to measure how close these vectors are, not just using Euclidean distance, but using the cosine formula from linear algebra. So it's a little more, I found it was a little more accurate to use this similarity measurement than just how close these points are in this space. And the way I measured the accuracy was we had a data set that was pre-labeled for us of non-functional requirements. And I ran the model through and saw how accurate it was at guessing what the right label for those was. And the way I did that was I used vector averaging. So what I did was we have a list of non-functional requirements. And those are just the labels that appear in the sample, the practice data set, really. So words like security, maintainability, usability. And what I did was I said, okay, how similar is the entire sentence to one of these topics? And then, so you take all of the words that appear in the sentence and you test them for cosine similarity to the topic word like security. And then we just get an average, which is going to be our score for a sentence. And we can reuse that in some other contexts. So that's how we extracted the NFRs from the corpus, was we had this canonical list that we decided on. We used 15 of them in the actual project, 5 for the practice project. And you can fuzz this if you want. You can take more than just the top score. I chose to just take the top score. I was trying to keep things simple for this project. And then the other thing we can do is, well, we can say, well, what if the corpus doesn't even, what if it has sentences that just have nothing to do with software whatsoever? If it's an interview with your client for a software project, then you might have asked someone to go get you coffee, and you don't want that to appear as a software requirement. You don't want your software giving you coffee. So what I decided to do was I compiled a list of words that have to do with software. And this was a little less accurate than extracting the NFRs. When I ran it on the actual project, it ended up thinking that absolutely everything was related to software in some way, which was very much not true. But it did no harm. I talked about using a practice data set to decide whether this was worthwhile, but I still wanted a way to figure out if it was actually safe to label them. So what I ended up doing was I just used standard deviation, 1 or 2 standard deviations away from the mean. If it's too high if it's very high, we can be very confident. If it's very low, we can be pretty sure that we can get rid of it. And I apologize if anyone is colorblind, both of the professors on this were, but I promise the colors do not matter. So this line is the mean. This is first standard deviation, second standard deviation, and this is just the best topic averages. And yeah, these are results where it got the label correct. And you can see a lot of times it was very, very not confident about it, but all of these are actually correct. It guessed the original label on the test data set. So got 95% accuracy if I took the second standard deviation. Not pictured on this slide, so you'll just have to take my word for it. If I went above the first standard deviation, it was 66% accurate. So we decided that that was probably good enough to move forward. It wasn't as good as some of the other ways that they had labeled the NFRs in the past, but we needed to move forward a little bit to get to the real meat of the problem, which was labeling the functional requirements. So, we don't really need that slide. So, I already talked about, we extract the NFRs, then we extract the words, the sentences that have nothing to do with software. And then what we're going to do, there are some equations in here that aren't really important for this presentation, I'm sorry. But one thing we want to know though is whether the topics we get out are any good. And there's a formula to get something called the UMass score, and this is just a numerical representation of how good the topics are, how coherent they are to the database as a whole. And I said that we could specify how many words we want per topic, how many topics we want, and you can see that as you add more words and more topics, it gets less coherent. This makes sense. If you are no longer picking an absolutely fantastic word to describe your corpus, it's probably not going to, it's going to get more, it's going to get less coherent as you keep adding more words that aren't as good. It's going to get less coherent as you add more topics that aren't as good. This is also going to be a problem that we'll look at later. So the question was, is it any good? And the answer is no. And this is part of why I was a little surprised that anybody wanted me to present this project. But this has gone through a data set that was entirely requirements for software. So there were no sentences in this entire database from West Virginia that had nothing to do with software. So if it ever discarded anything that had from looking at those software words, it was wrong. That's the first problem. The second problem is it put all of these sentences into one topic. And you can see down here, there's all these empty topics. And that score that data set, the labeled data set that I just looked at, that was the most coherent score that I got out of this database, out of this data set. And there's, so then what I did was I ran it a second time. And this time, instead of doing this thing where I look at the cosine similarity, I just used the built-in similarity function, which is a guided words model. It looks at whether a topic word appears in the sentence and applies a weight to it. And Jensen does that automatically. And you can see this time, well, it did put some sentences into more than one topic, but leaving employee track authority, well, a lot of these topics actually contain the same word. So this is another problem. It turned out, and this is not something that you would think would happen all the time, but it turns out that you can actually have exactly the same topic, but all of the weights have the opposite sign. So you have one topic where it wants to put any words that appear in that topic, it wants to shove all the sentences there, and then other sentences that have nothing to do with those words, it wants to get them as far away from that topic as possible. But the topics themselves contain exactly the same words, which is a huge problem for the bad words version of the model. And it also turned out to be a big problem for my cosine similarity idea, because that one, well, if a sentence had anything to do with the best topic in the entire corpus, well, it wanted to put every single sentence in the corpus into that topic because that was the best topic to describe everything in the corpus. And if something ended up in the polar opposite version of that topic. Well, that's because it was just nonsense. It was sentences like just ellipses or something that didn't make any sense whatsoever. Maybe words that the model didn't recognize as being words at all. Yeah, so when I originally saw that it was shoving everything into the same topic, I actually thought this was bugging my code, but it turned out that that's what was going on, which was a little disappointing. We don't need to talk about the code, so any questions? But I'll ask questions. Or one question?
Yeah, take a question if you want. Anybody have any questions?
Given that you said it didn't work for you, what direction would you take if you did it again?
Right. So I actually think the method I chose to label the NFRs, the cosine similarity over a good topic word, like the list of NFRs, I actually thought that worked pretty decently. I wasn't really disappointed with that, and it also showed some pretty promising accuracy if you took a very confident score from the practice database. And in particular, I think that can work as at least a starting point for the engineers. I think it can also work as a verification if you have another method of labeling the NFRs. Like one of the ways that we did it was using a neural network to learn pretty much word vectors, and it would learn how to categorize the sentences that way. But yeah, unfortunately, the method I chose of labeling the functional requirements with the topics was really robust, and that was the meat of the project. So that's why I said it was a failure.
Thank you, John. Next up is Tian, an asynchronous distributed deep learning based intrusion detection system for IoT devices.
Thank you everyone for letting me have the chance to share my research with you. Yeah, so my topic is about how do we do intrusion detection and then a distributed environment. And the contribution we want to make is about how to update the parameters asynchronously. First of all, I would like to give you some background things. Because when we talk about the IoTs, it means that Internet of Things. It means that instead of the connection of traditional devices, we just connect to everyday like physical device such as like a smartwatch or smartphone, or even like using our home appliance or even our shuttle. Yeah, one example here we want to see is like, for example, in our school we can have our apps to keep track of our shuttle. Yeah, that's an example. So here, but however, when IoT gives us makes our life convenient because it helps us to collect more useful data, I mean for use, the security issue is very important. So we must, when we take advantage of IoT, we must try to have some security mechanisms. Here, so our design goals is like the IoT intrusion detection system should be effective. When we talk effective, it means that because we have more and more devices, they will have more and more protocols and different standards. So we must have some way to figure out all the patterns of those new complicated protocols. And the efficient is the most efficient. For IDS system, it should be quick enough. Here, I will give you some introduction to some existing IDS models. The very classical one is like the knowledge-based. The knowledge-based is just like we make rules for them, and then after that, when we do the detection, when it triggers a rule, it just labels as maybe a malicious behavior. This method is very fast and easy to implement in some way. However, the thing is like this technique is vulnerable to new attacks, or attacker can change some details of the attack, and so then the system will be invalid. The second thing is like, as I said, the Python is increasing very fast these days. It's very time consuming to create, the rules manually. To solve the problem, some people proposed like machine learning method. Machine learning method, it builds statistical model instead of creating all the rules manually. In this way, it has approved adaptability. However, the downside of it is like, for example, if we do that in a single machine, even like a machine with like GPU or something, it still requires significant computation resources. And the second thing is like, if we want to do the analysis of all the data in a single point, we must transmit the data to that point, especially in some network environment. It's impossible. So in this way, some people actually proposed like a concept like federated learning model. In this model, actually it has two submodels. Here I want to say the general synchronous one. In the synchronous model, instead of putting everything together, they have a lot of distributed nodes. Here I wrote it as agents. Those agents actually they are distributed actually in the whole network, and then they can just collect the data locally and then treat them locally. And then after that, because when they're distributed all over the network, actually they need to work collaboratively. So they just transfer all their parameters to a central federated server, which is also called as a parameter server. Then the parameter server just does the aggregation and then puts the global parameter back. The thing is like this. However, in the synchronous model, here the central server, in each iteration, it will wait until every single node, or nearly all the single nodes, when they transfer their local parameter update to the server. In this architecture, it makes like it reduces the amount of data transfer significantly. However, the thing is like, because the network environment is complicated, some nodes maybe their performance is not good, maybe the network is not good, so maybe the performance will be impacted negatively because of those slow nodes. So to overcome this problem, some people just propose like a synchronous model. So a synchronous model, instead of waiting everyone to upload their local updates, actually the server just does aggregation. Once a single node gives it the local update, so it doesn't have to wait for all parameters to be uploaded. However, the thing is like, it seems good, but it can cause the stillness problem. The stillness problem is like this, because as we see, because when we do the gradient descent, or we do the stochastic gradient descent, we need to update it based on the last iteration of the parameter. However, if we do it asynchronously, this will cause some problem. So if we see like work I'm and work I'm prime, at one iteration, it gets the global model WT, and in the iteration then the I'm prime, it gets T+1, and then they both do their local update. After that, when the worker I'm then has gradient, and then it pushes to the server, to the parameter server for the global update. The now the global parameter is like WT+top. However, this one actually, as it gets the parameter before, so it's still working with the with the delayed wait, After that, when this one uploads its gradient to the global prime server, actually it's delayed. Here, I show you like this. Usually, for example, if we want to get a t plus tau plus 1, the w is a parameter. Here should be t plus tau. And this actually here should be t plus tau here. But however, as a matter of fact, this we just use t, and the eta is the learning rate. So the stillness problem actually it can makes more iterations to for the whole loss function to convergence, and then the second thing is that sometimes even it can cause divergence problem. So existing solution for this, some people they just try to find an approximation for this, approximations to compensate the difference, or some other they just propose some kind of like adjustment functions based on the iterations, the delay, and also the loss function. And then the third one is like because they try to avoid this and to reduce the effect, and then they just try to compress the parameter. So it's just like a communication optimization. So after we talk about the structure we use, and then we will talk about like after we have the model, we will have to talk about the concentrated algorithm we use. For this one, actually, because as I said, the pattern is complicated, so we will use neural network because it can handle the nonlinear complex patterns better. And then because actually the neural network, it has many kinds of implementations. Here, this one for the intrusion detection, we will use autoencoder. Because autoencoder is like a neural network structure. It tries to reconstruct the input in its output layer. It first uses the encoder to map all the input into a latent layer using this encoder function, and then it tries to recover it from the latent layer with this decoder function. And this function here is like the activation function for decoder, and this is the activity function for the encoder. Usually we can use like function like a sigmoid function. To train each machine model, the machine learning model, we need to have like a loss function, because the loss function measures the difference between the output and the desired output, the original output and the desired output. The goal is like we want to minimize it. In our case, we will use the RMIC. Here I give you how it's calculated. So when we do the training, our goal is to minimize the RMIC value, because with value, it can reflect the model we push into the autoencoder better. Yeah. And then for the execution phase, for detection, we need that a smaller value will indicate a higher possibility of similarity for that category. Here, when we see, for example, when we have when we trained like some cases, when we put xi plus 1 here, when we got RMC here, we can have a threshold. If thresh and the RMC is smaller than threshold, it can be like a normal data, because if we treat the model with normal data instances. In our case, actually, we set up the threshold to 0.45 yet. Yeah, because after some experiments, we found this was like we can have a better result. Here, after we give you after I introduce the neural network structure we use, here I will use like how to handle like the delayed parameter problem. Here, actually, I tried some method. Actually, this one is like they just try to make a approximation by using this part to calculate how much it is delayed. Actually, at first, it was originally proposed for image classification with the residual network and for AE. Yeah, and then we for this error, and then later we just adopt it. I mean for autoencoder structure here. You see here, just as I showed before. Besides this one, it also uses this part actually to make the estimation. So here, in terms of experiments, actually we chose like the CIC-IDI's 2017 dataset. Actually, this is like a relatively new dataset. Yeah, and it's an upgrade based on the KDD 199. And for the training data, actually, because actually it has more than 100,000 normal dataset, actually we just pick up about 100,000 from the Monday dataset. And then to test it, actually we choose like another 200,000 normal data as well as abnormal data. For the abnormal data, we use the DDoS instances because although it has some other kinds of attacks. This DDoS it has the biggest number. So I think I want to choose more examples. Yeah. So then for the experiment setup environment, actually I use like one parameter server and 4 clients. After I export the data into the neural network, I used like 77 features as input, and then for the latent layer, I just take 75% of the input layer dimension. So it's 55, and then to do the update, and for each client, I mean each agent, I do 50 iterations of local updates, and then it requests just for global aggregation. Actually, I did 20 aggregations of just the global updates. After I run in 2 models here, under the blue line, it shows like with the aggregations how the training error goes down, and then the other line it shows as the asynchronous model. From this we can see that the synchronous training is more smooth and more faster, and the performance is better. But the asynchronous one, at some point, is fast, but at some point, it's not that stable. Also, finally, it's a little higher. The training error. And then after we have the model, we just we just tested all the instances, and we used all the 4 metrics here. And then as we see, we get this result. We can see that the synchronized model, the performance is a little worse than the synchronous one, but at least it still works. Yeah, its performance is not that bad. So here, after our work at this moment, we figure out that the deep learning network, like an autoencoder, can be used for intrusion detection, and we also tested the asynchronous parameter update method for this. Yeah, we also tested with some new data set. Maybe in the future, we will just try to optimize the asynchronous parameter update method. Because although it works, we adopt it, but we found that if we do maybe many rounds of aggregation, this method, it may cause some overflow, because maybe the bitwise product of those those parameter vectors. So we need to find a way to improve it. Then we will test more attacks. And then, we need to give a full theoretical analysis for the convergence, to make it like more reasonable instead of just like experiments. Thank you.
Does anyone have a question?
Can I just ask what your 77 features were?
Oh, the 770 features. So for example, it may be like the port number, like the length of the header, or like the type of the protocol, or maybe like the flags in the in the packet. Yeah, something like this. Yeah. Thank you.
How's the
inputting data quality? You have recent data?
No.
Your data source know any recent data?
Sorry?
Your data source inputting data know any recent data?
No missing data yet. Because actually they have the raw package, they also have a formatted one for machine learning training.
Next up is Yishan discussing Fortune 500 company performance analysis using social networks.
Allow me to make some adjustment to the topic, is exploring correlations between segment of environmental threats and the stock market, because we didn't actually use the whole list of the Fortune 500. So my name is Yishan Shi. I'm presenting the project that we've been doing for the past semester. And this project is done under the supervision of Dr. Jen, who is not here today. And Jon Patton, who just presented, also contributed a lot on this project. So I'm now a newly graduated master in computer science from with data science track in Towson. And before coming to Towson, I studied literature as an undergrad and culture and anthropology as a grad student. So start this. I'm going through the I will go through the motivation of this research and the tools and approaches we're using and how we collected data, both Twitter data and stock data, and how we did sentiment analysis and the analysis of correlation between tweets and stock price. And there will be a conclusion. So this research idea was brought up by Dr. Okajima and Dr. Nick from Department of E-Business and Technology Management here in Towson. So there has been an abundance of studies in the past decades proving that public sentiment extracted from social media has the power to predict the fluctuation of the stock market. But most of the studies use the social media data as a more general data. Like, for example, we're using Twitter data. So it might be tweeted, all the tweets posted within a time frame. So, but what if we narrow down the data set from general data set into more specific one? Like, what if we only want to look at the environmental related tweets? So that is, we want to know what would happen if we're only extracting tweets with containing some keywords that we assume is environmental related. And does it still have the power to predict the stock market? So we decided to extract Twitter data over 5 years from over 100 major companies and filter them. The 5 years from 2013 to 2017, because that correlates to the stock price I can get. And then we want to see if the sentiments in those filtered tweets can still predict the stock market. So this project was run on Ubuntu, and our the main scripting language we're using is Python 3. We also use SQL, and our data are stored in my SQL database. So the analysis approaches are natural language processing, especially sentiment analysis, and we also build some machine learning models. So now we have the tools and the questions. Now we want to locate our target enterprises. This picture is some people protesting against Shell, because Shell planned for drilling in the Arctic. So lots of people is protesting against that, and Shell stopped that plan in 2015. So we have two different sets of our target. The first one is the top 100 from the Fortune 500 list. And the second set are some enterprises that I filter out through browsing through news and the website of environmental NGOs. Those enterprises are this company with significant, usually notorious reputation on certain issues. And they usually have a lot of Twitter accounts. So we just collect data from the accounts that tweet a lot. So these 5 categories are the IT industry, which is also debatable on energy consumption. Google is a counterexample that Google has announced the achievement of the 100% renewable energy usage in 2017. And oil, which include Shell, BP, and Exxon, and some companies have been accused of using illegal palm oil from illegal sources, like Nestle, J&J, and Unilever, and the drink companies who produce lots of waste, and the fast food company that are using meats from illegally deforestation sources. So in total, this is over 100 companies. So now we have the list of our targets. We want to collect data from Twitter. There are two different ways to collect Twitter data. The first one, and the most popular one, is Twitter has an official API and a corresponding Python library called TweetPy. But the downside of this one is that it only allows you to get data from the past 7 days. So that means if you want 5 years of data, we have to collect data for 5 year minus 1 week. So we'll just skip that. So the second way is that Twitter has a powerful web tool. It's their advanced search web. So we can get all the data we want from this page, but we don't want to click mouse to do that. So we can write a script to get those data. So we obtained the source code from GitHub thanks to Jarvis and Henry, and we made some adjustment on the script to make it fit our needs. But the downside of this one is because it's a customized script, we can just change anything we like. But the downside is that once Twitter changed anything in the structure in their JSON object, we have to change the script too. So after getting the Twitter data, our raw data is nearly 6 million tweets from 158 accounts. And we created a big table in the MySQL database to store all the raw data. And we filter the data with a list of environmental keywords and put them into separate tables according to username. And we also have a separate table to keep track of the stock ticker corresponding to those Twitter accounts. And this is a screenshot of Shell's tweets. And after we have the raw data, we want to filter it to make sure that we're using only the tweets that we assume is environmental related. So we tried the two different ways to filter data. The first one is just filter with Python. Just scan through every entry of the tweets to check if the tweets include some of our keywords. And this method runs very fast, and it keeps as much data as possible because we are not giving too many restrictions of the filtering. But keeping data as much as possible means the accuracy is lower. But we can, if the amount of data is not very large, we can just browse through the data to decide if we want this filter or not. But our data is 6 million, so we decided just let it go. We're not going to examine like one entry by one. But there will be some question, like Google tweets a lot about how they recycle their Gmail accounts, and recycle is one of our keywords. And I also tried another way to filter the data with SQL. So we set up a more strict format of the keywords. Like we want this keyword, and we set up the order and the form of these keywords. And we have a very high accuracy with this method. But the problem is that after filtering, the data will be very sparse. And we will suffer from data losses, and it runs really slow in the database. So in the end, we decided to go with the first one, just keep our restriction looser and use Python to filter data. So after filter, this is some example of some keywords. The actual list is much longer. It's just a small part of it. And after filtering, we have about 68,000 tweets from 154 accounts. And this is the amount of the tweets after filtering. As you can see that there's no tweets here. the distribution is highly sparse. It's highly uneven. And this sparseness will create some problem when we're doing our analysis. And we have to deal with it later. So now we have the Twitter data, we want to get stock price data. And I found this online database very useful. Quando is a partially free database. And they have an official API, they also have a Python library. And because of the daily stock price we want is free, so yeah. This is the database that I'm using. So we have the Twitter data and the stock price data. Now we want to do segment analysis on those Twitter data. So I tried two different approaches to do segment analysis. The first one is using Vader. Vader is a segment analysis package included in Python NLTK library. It was published in a paper in 2014. And in that paper, the authors claims that Vader achieved 96% accuracy on tweets. It's extremely high. And the good thing about Vader is that they already written all the NLP works for you. So you just pull a text and throw it into Vader, and it gives you a sentiment. And another way is that I use scikit-learn to build several machine learning models. But in this way, because we're building our own model, we have to have a set of training data, and all the input data has to be pre-processed. So this one is more complicated. So it's Vader. Like it runs so fast. Like it's like 5 minutes for 6 million tweets, and it clean the text for you, and you weight your text by a list of booster words, and you assign segment score to each word according to their own lexicon. The output will be a normalized compound polarity score from -1 to 1. And because I want to incorporate the output of Vader with the output of machine learning models later on, so I also mapped the polarity score to 3 different categories. It's positive, neutral, and negative. But the threshold of this mapping is adjustable. You can do it by yourself. And to use machine learning models to do segment analysis, we have to first clean the messy tweets people posted. So I clean the text by converting all the tweets into lower cases and removing additional white spaces and removing the repeated characters and replacing all the URL mention and hashtag with stop words. And then we remove all the stop words that map all contraction to their original forms, like I'm will be I am or you are, something like this. And after all this cleaning, each entry of the tweets will be just a list of cleaned words. They will append those words to the feature vector. So the feature vector will look like this. On the left side will be the cleaned words, and on the on the right side, if it's training data which is pre-labeled, there will be the sentiment like 0 present negative and 1 is neutral and 2 is positive. So this is our raw feature vector. So then to build a model, we need training data. So I got 1.6 million tweets, pre-labeled tweets as our training data. And the main sources is Sentiment 104. I believe it's also created by Stanford. And another database called Crowdflower's data for Empirical library. They also have some pre-labeled tweets, so I just combine everything together. And each trend data has a sentiment number, which is positive or negative or neutral. And now we have trend data, and we have a way to get feature vector. We want to weight this feature vector. And I use 2 different ways, 2 different feature extraction methods to weight those vectors. The first one is backup words, like Jon just said that. Backup words is just care about the occurrence of the words regardless of their order. And the second method is TF-IDF. The basic idea behind TF-IDF is that if a word appears a lot in one document, then that word is very important in this document. But if a word appears a lot across all the documents. It might be just something that is not important at all, like the or. So we're using two different ways. So now we have a way to weight our feature vector, and we have training data. We also have an input data, which is the raw tweet we downloaded from Twitter. So I built 3 kinds of models. The first one is multinomial, noise-based, and logistic regression, and support vector machine. There was a fourth one of random forest, but random forest just runs forever for just a depth of 10 trees, so abandon that one. And all the models gives out an accuracy around the 77%. I think that is acceptable, so just keep that. But I don't want 6 outcomes, it's too many of them. So I take mod of, like for each method of feature extraction, I just take the majority of them. So for the output from machine learning, now we have 2, like 1 for backup words and 1 for TF-IDF. So in total, we have 3 different results. One is for using backup words, and one is using TF-IDF, and another is data. And you can see that no matter which method you're using, we have much more positive tweets than negative or neutral tweets. And that is one problem that we haven't thought clearly when we started this project. That is, we are using the tweets tweeted by the official accounts of these companies. And these accounts are used to build the public image of these companies. So it's reasonable that they will tweet more positive things rather than negative things. So now we have the sentiment data, and we also have the stock data. We want to combine them together. But when combining the stock data and the sentiment data, there's one thing to note, that there's a time lag between the tweets and the stock market. Like from previous studies, people suggest that if you tweet something really negative today, then 3 days later, your stock price will drop. And some people say it's 6 days. So I'm not sure which one's better, so we just try from 1 day to 7 days. So this is a sample of the data that we have merged everything together. Like those are all the stock prices, and this is the date of the tweets, and this is the date of the stock price, and those are the sentiments. So then the first analysis we want to do is linear regression. But usually sentiment data on Twitter is treated as time series. But after filtering, our data is so sparse, it is not reasonable to treat it as time series. Then how can we do this analysis? So an experiment that I came up with is to try to fill this sparseness by combining all the data together. So, but like each company have a very different number of their stock price. Like some is wandering around 300 and somebody wandering around 50. So I try to normalize them by taking like why is the original closing price of a day. Then I minus the annual mean of that stock, and then divide it by the annual standard deviation, and got an output as a normalized closing price, and which will represent the fluctuation of the stock price comparing to the whole year's stock price. So that way, all the stock price, no matter which company they belong to, will become a number between negative 0.5 to 0.5. But the variance score is 0, which means that we cannot see a clear correlation by using linear regression on combining all the data together and the stock price. But when we try to visualize the output, there might be something that we can say about those orange dots. Means that the majority of tweets on that day is negative. and the green dots means that it's positive. And this is the resolution is not good. And this plot is from Google, like the day lag between tweet and stock price are 2 days. And this is the first half year of 2015. So you might notice that some of the drops in stock price correlates to the orange dots, like in this purple rectangulars. So this is Google and this is Johnson & Johnson. It's the same thing. You can see some dropping points with orange color. This is McDonald's and Pepsi and Exxon. So we believe that the correlation between segment of environmental tweets and the drop of stock price might still exist in some cases. But the problem is that our data is so sparse, we haven't found the correct way to describe it. And there is also some issue in this, something that like I mentioned, most tweets tweeted by official accounts are positive. So we have a sample bias. And while dealing with those data, I noticed that the fast food companies and those companies like Pepsi and those drink companies, they don't care about environmental issues at all. The accounts that they have is to build an image that when people saw the logo of Coca-Cola, they will think about happiness. They won't think about anything else. That is it looks like it's the public image they want to build. So some company is not using Twitter as like each company have a different focus on using Twitter. So like we have that is another sample bias on the purpose of this Twitter accounts. So this is just a preliminary experiment, and there's a lot of future work to be done. The first is I want to improve our filtering strategy to make it more accurate, but without suffering too much data losses. And we might explore other analysis models and plotting strategies to find out more outputs or more correlation or interesting things to do. And because we're only using tweets tweeted by company accounts, we should add tweets by other users that is mentioning about those companies. And another data set I have already collected but haven't used are tweets tweeted by environmental NGOs. I think they have, in certain cases, that they might have a strong impact on how people think about those companies. And we may also incorporate social network analysis approaches, like if we have a data set of all the users mentioning about Pepsi, then we might group those users into communities and find the most important user or the active users and to observe how this user interact to the company account and how do their influence spread. And that way we might find something else. So that's the end of my presentation. Thanks for your attention.
So, because of the time, we can take one question, and afterwards we can talk to the speakers. Does anyone have any questions?
How do you choose content? How do you choose content?
Accounts?
Yeah, how do
Twitter
you
accounts?
How do you make choice?
So for each company, they will have a lot of accounts. So we're choosing those accounts that is active, means they are tweeting a lot. Like Google has about, I think Google has about 200 accounts, but some of them is not tweeting. So we don't use those kind of accounts.
Okay.